All right, we'll clear up a little, perhaps, misunderstanding. We've been dealing with a couple of scenarios here with Gauss's law. So let's talk about Gauss in a conductor. Now, I think everyone loosely knows that a situation such as the following, let's say this is a metal sphere. Let's say it's hollow. Let's say it has a charge of plus Q on the surface. Everyone knows that inside, let's say this thing is of radius capital R, the electric field inside, which effectively means the electric field when R is less than big R is going to be 0. And if we wanted to be more formal about it, we draw ourselves a little Gaussian surface inside, and when you set up your E dot dA equals your Q enclosed here, there's no charge enclosed, it's going to be a 0 over E naught. Clearly, the area is not going to be a 0, and this results, of course, in the same thing, that the electric field inside is 0. Fine, I don't think there's much confusion about that. Where there may be some confusion is a situation that's similar, like we saw on the homework. Maybe we have a plus Q, and let's give this thing actually a little bit of thickness, like we saw on the homework. But in the center, we're going to put a charged object. And we'll make this one, doesn't matter, call it also plus Q. Now, the possible misunderstanding here is, well, inside a conductor, the electric field should be 0. So, well, what's going on here? Does that mean that if we draw a Gaussian in here, that within that little green area, that the electric field should be 0? Well, the answer is no, it would not be 0. So let's put this at some radius R. And so if we ran Gauss's law, E dot dA Gaussian equals Q enclosed over E naught. And we're going to look at this over that small r. You know that your electric field is going to be constant spherically here, so we can pull that out. And the dA, they're going to be perpendicular, so the surface area. And so the area vector and the electric field vector will actually then be parallel. And so the dot product comes out, and you end up with EA equals, we already know the Q enclosed here is positive Q over E naught. And then, of course, your area is just a spherical surface area, 4 pi r squared. You can rearrange this and you get your answer. Not a big deal. That math is very easy. The issue, though, is, well, wait a minute. What do we mean here when we say that the electric field in a conductor is 0? Clearly, in this hollow, it is not 0. There's an electric field, as you can see, based on that positive Q, that runs outward in this direction. Oh, that was a little too far. Radially outward. And so you may feel some sort of conflict. However, there's a bit of a misunderstanding here with the naming. So when it says the electric field in the conductor is 0, what they're talking about specifically is in the thickness of the conductor itself. So if we take this same picture and we try to redraw it a little better over here, so we'll have our inner radius and our outer radius. We'll make this a little more conducive to manipulation by drawing. And so we still have our positive Q right here in the middle. Now, this distance right here can be our R1, or Ri maybe for our inner, and Ro for our outer. And we can put a charge. We can keep the plus Q out here on this. The plus Q, we say that the electric charges, the electrons, will only move to the surface. So in seeking electrostatic equilibrium and electron-electron repulsion, the physical mapping that allows them to maximize the spacing between each other is actually to spread over the surface of the conductor. This conductor has two surfaces. We'll highlight them. We can have the outer surface. Actually, we'll use our little highlighter. That's good. Our outer surface is this one. And our inner surface, let's do this one. Okay? Now, charge can accumulate both on that blue outer surface and that pink inner surface. In fact, what happens here, this requirement that the separate note, the electric field inside the conductor equals 0 is literally referring to within the conductor. And what do we mean within the conductor? Well, if this, let's highlight it again, if this yellow area refers to within the conductor, then that's where the electric field's going to be 0. Not at the blue, not at the pink, not at the surfaces, but within the conductor. So if we draw, and this actually gives us a lot of power. If we draw, this is the within the conductor highlighter. There we go. Our Gaussian here. Okay? At that location, let's give that a new R. That's a green R. We'll call it RM for R middle. We know that at, let's see, at R in the middle, we know that the electric field is going to equal 0. How can this possibly work out? Well, here's how we use Gauss's law in reverse in some regard. So E dot dA equals Q enclosed over epsilon naught. Since we know that in that mid-region no charge accumulates and that the electric field will have to be 0 at that location, well, that actually forces us to adjust the left side of this equation. That tells us that 0 equals Q enclosed over epsilon naught. Of course, that's just a constant, so that will go away when we multiply both sides. That's telling you the enclosed charge is 0. Well, how is that possible? From what we see on the paper, the only enclosed charge here is that red plus Q. So notice here, we're working this in reverse. The first scenario you did way up top, here, we knew that there was no charge enclosed, which then allowed us to demand that the electric field be 0. Down here, we know that the electric field at that R mid, Rm, is 0, which allows us to then demand that the Q enclosed be 0. But we know for a fact that Q enclosed includes plus Q, the red plus Q. So how is that possible? Well, the only way this can be true is if, so this equals plus Q, there has to be a minus q. There has to be a minus q. And where is that minus q? Maybe that's a bad choice of colors. Where is that minus q? That minus q accumulates exactly where we drew it, right here, on the inner surface of that sphere. That is the minus q. And so, in fact, what happens in these scenarios is that the charge within the sphere's meat moves about. Some of it accumulates on the inner surface, some of it on the outer surface. And so in this case, what actually happens, if we redraw this, what actually happens is you will have still a net charge of plus q on the sphere. However, charge will move about such that you actually get a negative q on the inner surface. So that's along here. And you get not a positive q, but a positive 2q on the outer surface out here. Of course, combining those two, negative q and positive 2q, still leaves you with positive q. So we certainly have conservation of charge here. That is not violated. But the charge moves around such that the electric field within the conductor remains zero. And the only way that can happen is if the q enclosed within that Gaussian we just drew there in the green, that must be zero. The only way that can happen is if some of the charge from the sphere goes to the inner surface, in fact, exactly the amount opposite to what is contained within that hollow. And so notice here, the hollow, and this is kind of the point of all this, the hollow does have zero electric field if there's no charge enclosed. But if there is charge enclosed, the hollow does not have zero electric field. It is, in fact, when we say the electric field inside the conductor, we actually say within the meat of the conductor, so to speak, the electric field will be zero. Okay, hopefully that helps clarify some of these scenarios that are going to come up.